Welcome to this explainer. Hardware teams rarely struggle because they lack ideas. They struggle because the path from an initial requirement to a clean, reviewable design package is, well, let's be honest, it's notoriously messy. It's a real headache. But today, we're looking at how Traceai V1 completely compresses that path. We're going to see exactly how this platform takes raw engineering intent and turns it into a structured, reviewable handoff package in literally minutes. So let's dive right in. Here's our roadmap for today. We'll quickly examine the hardware design bottleneck, walk through Traceai's new stage-based workflow, explore hardware candidate architectures, look at designing electrically meaningful boards, and wrap up with exporting the final engineering handoff. All right, let's kick things off with Section 1, the hardware design bottleneck. If you've ever worked in electronics, you know this pain intimately. Early hardware design is incredibly scattered. Your requirements live in fragmented text documents, architecture debates happen in random spreadsheets, and there's absolutely nothing quite like the misery of digging through a 50-deep email chain just to find a single updated voltage requirement, right? But check out this insight from CircuitMind's research. It states that 70 to 90% of cost is locked in by upstream design choices. Think about that for a second. Up to 90%. The anchor components you pick on day one completely dictate your power requirements, your thermal behavior, your life cycle, and your budget. BOM optimization is an engineering problem. It is not a procurement one. If you're waiting until the schematic is done to think about your bill of materials, you've honestly already lost. So that brings us to Section 2. A new stage-based workflow. Traceai V1 takes all that early-stage chaos and organizes it into a linear, predictable path. Now, let's be absolutely clear about what this is. It is not some generic chatbot. It's not a magic black box that promises to replace human engineers or fully route your PCB layout for you. Nope. Instead, it is deterministic hardware intelligence. It's a powerful engine designed specifically to get you from requirements to a highly structured design package, while keeping you firmly in the driver's seat for the final layout. The entire workflow is built on 4 explicit product stages. Stage 1 is capturing requirements. Stage 2 is generating and ranking AI candidates. Stage 3 is reviewing the board design. And Stage 4 is producing that final design package. This structure keeps your momentum moving forward and makes the boundaries between automated synthesis and human engineering crystal clear. To prove how well this works, let's anchor this in a concrete, real-world scenario. Imagine your team is starting a complex industrial board. Instead of kicking off a messy email chain, you just enter your strict power constraints, your performance targets, necessary interface protocols, and safety regulations right at the very start. Traceai handles all of those constraints through a single shell cockpit. This unified engineering workspace takes your functional intent and your operating context and prepares to route it through its deterministic solver pipeline. And the best part? You don't have to bounce between 5 different software tools to do it. Moving right along to Section 3, exploring hardware candidate architectures. Now this right here is where Traceai really separates itself from basic diagram generators. It doesn't just spit out one single answer and force you to accept it. Here's the paradigm shift. The old way meant spending weeks, literally weeks, manually exploring maybe 1 or 2 viable architectures simply because it was way too labor-intensive to evaluate anymore. The new way? It gives you multiple fully ranked hardware candidates in minutes. It exposes the explicit trade-offs of each path before you ever commit to a schematic. Because, as we all know, better hardware designs always come from comparing alternatives early on. As you can see, the system explicitly scores those trade-offs. The solver generates distinct hardware strategies for you. You can optimize for a balanced approach or push the solver towards minimum cost, minimum power, or maximum performance. For example, a min-power strategy might automatically select an ultra-low quiescent current regulator, right? While a min-cost strategy might swap in more affordable components. You as the engineer get to see the actual BOM cost and power penalties for each path, and then you choose the winner. It's kind of like having a superpower. You explicitly set your optimization goal right up front. From there, the system uses its built-in component catalog to evaluate millions of potential combinations, discarding incompatible parts along the way, and then presents you with the highest scoring candidate architectures that perfectly match your selected trade-off profile. Which takes us to Section 4, designing electrically meaningful boards. Okay, so once your candidate is selected, we move into the electrical implementation phase, and I really want to emphasize this point. We are no longer looking at a conceptual storyboard here. Traceai provides an electrically meaningful structure. It doesn't just guess, it understands real part compatibility, it actually evaluates the power tree, enforces necessary isolation constraints, and creates a real verification basis long before you ever open your ECAD tool. The design workspace relies on true pin-level connectivity. Traceai is generating named nets. It's validating power rails to ensure you don't have an overloaded regulator or a missing ground reference. It's inserting necessary interface contracts and even automatically suggesting decoupling capacitors and EMI filters. It is a true, robust engineering workspace. As you're reviewing these circuits, the system is constantly running an active-reactive pipeline in the background. When you're finally satisfied, Traceai seamlessly transitions from the active candidate review into assembling the handoff package. It gathers up the verified power tree, the BOM, and the circuit graphs to synthesize your tangible deliverables. And that brings us to our final stage, Section 5, exporting the engineering handoff. This is where all that upstream intelligence becomes a real, reviewable artifact that can actually be used by external ECAD tools. Just look at this impressive array of exports. Traceai doesn't just hand you a text summary. No way. It gives you a natively readable KiCad schematic file with symbol instances and global net labels. It gives you a complete bill of materials CSV with actual footprint data and manufacturer part numbers. It exports vector PDFs, an electrical rules check report mapping any remaining violations, and a full project bundle. I mean, this is validation-grade output that proves this platform is incredibly mature and completely ready for downstream integration. Furthermore, Traceai maintains strict engineering discipline throughout this entire process. It supports version package snapshots so you can easily save and restore your work. It tracks exact BOM deltas and interface deltas so you can see exactly how a design changed between revisions. And bet this, the entire analyze to export flow is protected by integration testing. That ensures your engineering intent successfully bridges all the way to a clean ECAD handoff without any data loss. So I'll leave you with this final thought. Are you still manually documenting scattered requirements and endlessly debating architectures in spreadsheets? Or are you ready to compress your engineering intent into a reviewable, mathematically validated handoff package in a matter of minutes? Traceai version 1 is the new bridge between your product ideas and your ECAD tools. It gives your team a faster path to a better starting point, with engineering artifacts that actually move your work forward. Thanks so much for joining me for this explainer.